Hey, welcome back. This is complex numbers in polar form now. Obviously the class is trig, and hopefully you saw in pre-calculus some complex number stuff. So it's the imaginary number I is what we're looking at. Anyways, in this section, what we're going to do is start plotting these things, and then because we're plotting them, we can kind of create a polar form for these values, and that'll allow us to do some interesting math. Okay, so there it is. Starting out then with just kind of a review of things from the past. The complex numbers, what are they, what do they look like, etc. They're all given in terms of this thing called the imaginary unit. Which is kind of like the number 1, but not really. The imaginary unit I is basically the square root of -1. Okay? And then if you square that, I squared is just -1. Complex numbers then are kind of a mix of real and imaginary numbers, right? So the standard form for a complex number, which they'll give the letter z to, is going to be a plus bi. Okay, so a is the real part, and then b is the imaginary part. Okay, so just an example of things that we did in the past: multiplication. So multiply these things. We had something like 7 minus 3i is one complex number times 2 plus I. The way to multiply these guys is just FOIL. So 7 times 2 is 14, the outer, plus 7i, the inner, minus 6i, and then last, minus 3i squared. We'll replace I with I squared. Replace this with -1. That's from our definition. Not a lot of definitions, but the only one we have here goes there. Okay, so we'll rewrite this, combine some terms along the way. 7i minus 6i's is 1i, so 14 plus I, minus 3 times, and I substitute in -1 for I squared. So this will be 14 plus I plus 3. 14 plus 3 is 17, and then plus I. Okay, and hopefully that rings some bells. Let's now look at graphing them. Okay, so we're going to graph these things on what's called the complex plane. So the x-axis will be the real axis, and the y-axis will be the imaginary axis. Okay, so the x-axis is now the real axis, and the y-axis is now the imaginary axis. And if we want to plot something like z equals a plus bi, or let's plot an actual one, right? Z equals 3 plus 2i, right? All you have to do is think of kind of like plotting the coordinate 3, 2. Okay, so 3 in the real direction, 1, 2, 3, and then 2 in the imaginary direction, and there it is. Okay, so z equals 3 plus 2i. Okay, so let's just look at plotting a couple of these. So the first couple of problems, plot the complex number in the complex plane. And let's plot them all on the same plane so we don't have to keep replotting. 1, 3, 7, 11, and 13. Okay, so number 1 is z equals 4i, 3, z equals 3, 7, 3 minus I, 11, 2 plus 2i, and 12, -1 minus I. Okay. Get some tick marks on here. Real axis, imaginary. 1, 2, 3, 4. I don't think we need to go beyond 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. Okay. The first number, it's really 0 plus 4i, right? The real part is just 0, and then the imaginary part is 4, so that would be 0, 4. Okay, so I'll just put 1 for problem 1. Z equals 3 is really the same as 3 plus 0 i's. Okay? So you're just going to move 3 in the real numbers and leave it alone. 3. Then we have some normal ones here. So 3 minus I, so 1, 2, 3 in the real, and then down 1 in the imaginary. So that's problem 7. 2 plus 2i, so 1, 2, and then up 2. That's number 11. And then negative 1 minus I, so negative 1 in this direction, and down 1. That's problem 13. Okay, so pretty easy, right? I think it is. Okay, now we're going to look at kind of the absolute value of these things. Okay, and absolute value is about distance. If you did not know that, that's what it is. So if you recall, we've worked with the absolute value before, right? So the absolute value of negative 3, we know is 3. But technically, you can think of it as a distance away from the middle, 0. So 1, 2, here's negative 3. The distance between 0 and negative 3, well, that's, you count, right? 1, 2, 3, it's just 3. That's the distance. So you can reimagine this thing as just the distance from the center. Okay. And that'll carry over here. That kind of idea carries over into this situation where instead of a center, because now we have 2 axes as opposed to just one, the real number line, we'll think in terms of kind of a distance from the origin. Okay, so the absolute value will be, if I'm given something like, let's say, z equals 1 plus 3i, so 1 and then 1, 2, 3, and they measure. The absolute value of z in this case will be the distance from the, well, here it's called the pole, right, to the point in the complex plane. And you can figure that out by using, triangles and the Pythagorean theorem, right? So here we have one side is 1, the other side is 3, just the components from the complex number, 1 and 3. And then to get, this Pythagorean theorem, right? So you go, all right, this value here is the absolute value of z. The absolute value of z squared is equal to 1 squared plus 3 squared, and then if you square both sides, take square root on both sides, you get the absolute value of z is the square root of 1 squared plus 3 squared, right? Which is then the square root of 1 plus 9 is 10. So the absolute value of z is 10. In general, all you have to do is basically take the square root of the component squared. So if you're given a number z equals a plus bi, the absolute value of z, the distance from the center, is the square root of a squared plus b squared. That's it. Okay, so let's look at some examples from the book. Find the absolute value of 3. And again, 3 is the same as 3 plus 0 i's. Okay. So to get the absolute value, you're just taking the square root of 3 squared plus 0 squared, which of course is square root of 9, which is 3. Let's look at number 7. So z is 3 minus I. Absolute value of that then is the square root of 3 squared plus negative 1 squared. Okay, so it'll be 10. Okay. So it's like the same problem we did, almost. Let's look at some more. Yeah, got some more. Number 11. It's pretty easy. It's just a matter of remembering, how to do this. on a test. So the absolute value of z here is the square root of 4 plus 4, which is square root of 8, which is 2 root 2. Okay, that means I just got an email. Let's look at 13. So I have z is -1 minus I. So the absolute value of z is going to be the square root of -1 squared plus -1 squared, right? Because this is the same as -1 plus -1 times I. So a is -1 and b is -1. So this will end up being the square root of 1 plus 1. Negative squared is positive. So that'll just be square root 2. Okay. Because we can plot it like this, we can get a polar form for all of these complex numbers, right? It may take a second to think about it, but let me show you the deal. Okay, so section 4 now, polar form for complex numbers. And this will be cool because we can do all kinds of neat stuff. It'll make multiplication easier and division a little bit easier. Okay, so anyways, let's look at the complex plane and put a point here. And we can kind of just give it a plus bi if you wish. So let's say this point z is a plus bi. So this is, this distance here is a, this distance here is b, and then r is the absolute value of z, of course. We're going to give it another name, we're going to call it the modulus. Okay? But anyways, if you think in terms of kind of triangles, right triangles, you can say to yourself, well, I know from the Pythagorean theorem, first off, that r squared is equal to a squared plus b squared. And then we can also get those formulas like we got for the polar coordinate system, the conversion formulas, right? So I note that, hey, cosine of theta is equal to opposite b all over hypotenuse, which is r. So I can rewrite b as r cosine theta. And then sine of theta is equal to, oops, I screwed that up, didn't I? So cosine is equal to adjacent over hypotenuse. Adjacent over hypotenuse. So a is equal to r cosine theta. And then sine, of course, is then opposite over hypotenuse. So b will equal r sine of theta. And so if you have a value z equaling a plus bi, you can always rewrite that as r cosine theta plus r sine theta times I. And that's not how we traditionally want to write it. We generally want to write it in the form r times, so factor out the r, and then you get cosine theta plus I sine theta. We like to put the I in front so people don't think that the I is accidentally inside the sine function. Okay, so it's clear that I is not inside the sine, because you may misread the other version, right? So if you think of kind of like a parentheses here, that would be incorrect. The parenthesis is actually right there, and the I value is on the outside of it. So to avoid that confusion, we put the I in front of sine. Okay, and that's the polar form for the complex number. You can also, and of course we also have the tan formula that can be useful again. So tan of theta is just going to be opposite over adjacent. And anything else I want to say? R is called the modulus now. But it's really just the absolute value of z. And then theta also, they call this thing the argument. And for us, we want to make sure that theta is in between 0 and 2 pi. Okay, that will just make life a lot easier if we make that convention. Okay, so first, a couple problems are writing in polar form, converting back and forth, basically. So first, given kind of the complex form, go to the polar form. So right and polar form. And then the other form, the form we're starting with, they're going to call that in the book I think they call it the rectangular form, weirdly enough. So anyways, the rectangular form is 2 plus 2i. That's kind of the form you're used to. And then we want to rewrite it in polar form. Okay. So first, the r value is just, the absolute value of z, which is the square root of, in this case, 2 squared plus 2 squared, 4 plus 4, which is root 8, which is 2 root 2. So this would be 2 root 2 times the cosine of some angle plus I sine of some angle. Okay. So to get the angle, what you're going to use is the tan formula. So tan of theta equals y, the b value over the a value. So 2 over 2, which is 1. And then we want to take tan inverse on both sides. And basically, the reference angle that gives you 1 is pi over 4. So pi over 4. It's definitely in between 0 and 2 pi, so we can wedge pi over 4 in here. And then over in here as well. Okay. And of course, there's another angle that would give you 1. That would be the 5 pi over 4 down here. But 2 plus 2i, if you think about where it is, it's in the first quadrant. So there's no way it could be the 5 pi over 4 version. Okay, so it doesn't hurt to draw a graph of where you are, just so you can keep things kind of straight. Okay. Okay, let's look at another one of these. This is number 17 from the book. So we have z is 2 radical 3 minus 2i. And again, we want to put it in polar form. So our r value, of course, is the square root of 2 root 3 squared is 4 times 3, which is 12, plus negative 2 squared is 4. So that's just going to give us root 16, which of course is 4. I'm going to have to get tan of theta, find the theta value. That gives me negative 2 all over 2 root 3. Okay, so that would be equal to negative 1 over root 3. And I want to make sure I get the right quadrant for my theta value. Okay. So 2 root 3 is positive, and then down is in this quadrant. So it's in the fourth quadrant, and the reference angle that gives me 1 over root 3 would be pi over 6. So I need the pi over 6 version that's in the fourth quadrant. So that would be our 11 pi over 6. Okay, then we could just fill in the material here. So it's 4 times cosine of 11 pi over 6 plus I sine of 11 pi over 6. Okay. And there it is. Okay, let's work with going in the other direction now. So we'll begin with the polar form and then go to rectangular. Okay, so convert to rectangular. We'll make this one the video quiz. So video quiz, video quiz, video quiz. Let me mark down in my notes. And actually, I think we're into a different homework set for the video quizzes. So our last homework set was number 4. So now we're in video homework 5. And this is 6.5. And the one we want to use is number 27. So all you have to do is convert it to rectangular form. I just needed to note that in my notes. And I will get right back to it. Okay, so hopefully this is the video quiz question, number 27. So I have 6 cosine of, and somebody in my office hours? Yes, no? Okay, no. So I have 6 times cosine of 30 plus I sine of 30. And now I'm going to convert it in the other direction. So this way is pretty easy. You can just evaluate the cosine and the sine here. So cosine of 30 degrees is cosine of pi over 6, which is root 3 over 2, plus sine of 30, of course, is 1/2, then times I, and then you just distribute the 6. Okay? So an easy video quiz today. 2 goes in the 6 3 times, so that would be 3 root 3 plus 3I. That's it. A lot easier, huh? All right, let's look at one more of those, just in case there's anything weird we have to worry about. 10 times cosine of 210 degrees plus, 210 degrees plus I sine of 210. Where is 210? That's down here in this quadrant. So cosine is negative and sine is also negative. So 10. 210 is 30 degrees basically as a reference angle. So it's the same numbers as before, except they're both negative. So negative 3 over 2 minus 1 over 2I. And then distribute the 10. So we get negative 5 root 3 minus 5I. That's it. Okay. It turns out that multiplying these things is a lot easier, in my opinion, if you're in polar form. Multiplying and division is a lot easier than the multiplication and division in the rectangular form, I guess. For example, back when we did division in this form, it was people always kind of screw these up. So like 3 minus 2I divided by 2 plus I. Do you remember doing these? What you should have to do, you'd have to multiply top and bottom by the conjugate. Then you would get, 6 in the numerator foiling, 6 minus 3I minus 4I, and then minus 2 times negative 1, so that would be plus 2, all over 4, the inner and outer cancel, and then minus negative 1, so plus 1. Then that would be 8 minus 7I all over 6, and then that would be 4/3 minus 7/6I. Okay, so division and multiplication. Turns out it may be a little easier, but you kind of have to remember how it works. I guess that's the trade-off here, but let's take a look anyway. So products and quotients. And 37, we want to do a product. And I'll kind of show you the reasoning as I go through this problem. In the end, there's a kind of a shortcut to it, but I'll show you why the shortcut works. Okay, so Z1 is 6 times cosine 20 plus I sine 20. And then Z2 is 5 times cosine 50 plus I sine 50. Okay, so Z1 times Z2, and I promise there's an easier way to do this, it's just we want to give you some sort of reasoning. Okay, so literally what is this? It's basically, I'm going to have to recopy. You may not even want to copy this down, just sort of watch. You can multiply using commutative rules. So you can multiply the 6 times 5 is 30. And then you're going to FOIL out the cosine 20 plus I sine 20 times cosine 50 plus I sine 50. Okay? So FOILing that out, you would get cosine squared 20 from the first. The outer would be so plus I times cosine 20 sine 50, the inner plus I cosine 50 sine 20, and then the last plus I squared sine 20 sine 50. I squared is just negative 1, so it's become minus sine 20, sine 50. Okay. Because, again, this is really I squared plus I squared sine 20, sine 50. And then you always replace the I squared with a -1. Okay. Can we simplify this at all? Not really, right? So what are you going to do here? You're going to use the couscous formula and the reverse of them. But first we want to kind of group the imaginary and the real parts together. So we have 30 times cosine squared of, well, actually you couldn't even say cosine squared, right? That's a mistake. This should be cosine 20 times cosine 50. I apologize. So it's cosine 20 times cosine of 50. Okay, so I'm going to have cosine of 20, cosine 50, the real part, and then the other real part is down here, minus sine of 20, sine of 50. Okay, and we could apply the couscous formula to that part, right? So this would be 30 times this thing is cosine of 20 plus 50. And then you have plus, and I'm going to factor out the I part. And what do I have left? I have a cosine 20, sine 50. And then plus cosine 50, sine 20. And you could apply the same sine formula to that. So you get plus I sine of 50 plus 20. Or 20 plus 50. Let's put 20 plus 50 just so we can kind of see a pattern happening. So what's the pattern? Basically, you're just multiplying these guys together, and then instead of multiplying out, you're adding the arguments together. Okay, so you'll see 20 plus 50 inside the cosine. That's right here. And then 20 plus 50 inside the sine right here. So it kind of turns a multiplication into a quasi-multiply and then a quasi-addition. Okay, so there's a multiplication of the moduli and then an addition of the arguments. So in the end, it'll become 30 times cosine 70 plus I sine 70. Okay, so in general then, if we have kind of R1 times R2, or sorry, Z1 times Z2, Z1 times Z2, that'll equal the modulus from Z1 times the modulus from Z2 times cosine of the argument from Z1 plus the argument from Z2 plus I times sine of the argument from Z1 plus the argument of Z2. Okay. Quotients kind of work in a similar way. I'm not going to go through the reasoning, the why, and the how. But also then Z1 divided by Z2 is just going to be R1 divided by R2. And then you could probably guess how the arguments are going to work. Instead of adding, you're going to do what? Subtract. Okay. So it's just it comes down to a matter of just remembering at this point rather than anything else. And you know, in the rectangular form, it was a matter of you kind of have to memorize a process. You have to multiply top and bottom by conjugates, or you have to FOIL. Here it's just kind of a memorizing of forms. Okay, so anyways, let's look at multiplying and dividing in number 47. We have Z1 is 3 times the cosine of pi over 5 plus I sine of pi over 5. And then Z2 is going to be 4 times cosine of pi over 10 plus I sine of pi over 10. Okay. All right, so Z1, Z2 is just going to be 12 times cosine of pi over 5 plus pi over 10. What is it? So you can find a common denominator, right? So this would be 2 pi over 10, and same for this one, 2 pi over 10. So you end up with cosine of 3 pi over 10 plus I sine of 3 pi over 10. And then the division problem, C1 divided by Z2, is going to leave you with 3/4 times cosine of 2 pi over 10 minus pi over 10 is just going to give you pi over 10. And then plus I sine of pi over 10. Okay. Okay. Let me make that look a little prettier. 3/4. Okay. The next thing to worry about then is raising complex number of the powers. If you think about raising something to a power like z cubed, it's really just repeated multiplication. Okay? So if multiplication kind of works by addition here in the polar forms, that's going to be you're going to have kind of a multiplication of the argument. Or sorry, an addition of, yeah, it'll turn into a multiplication of the argument. So let me just say that then, kind of with an example. So part 6, we're looking at powers of complex numbers. And we'll take a look at an example. 53, we have 4 cosine of 15 plus I sine of 15 degrees, all raised to the 3rd power. Okay. So how would that work? Well, it's just repeated multiplication, but then it'll turn into kind of, okay, so let me show you. 4 cosine 15, and this should be like this, sorry. Cosine 15 plus I sine 15 times 4, and I guess we don't need this parentheses out here, times 4 cosine 15 plus I sine 15 times 4 cosine 15 plus I sine 15. So what do you end up with? You end up with 4 times 4 times 4. In other words, you just cube 4 like you normally would. Okay, so it's basically 4 cubed. Okay, and then for the first two at least, if you were to just multiply this, you're adding the arguments, right? So you end up with cosine of 15 plus 15 plus I sine of 15 plus 15 times another factor of this cosine of 15 plus I sine 15. So what? Well, then if you multiply again, you're just going to add in another one. So right now I have 2 of them. 4 cubed, it's cosine of 2 times 15. It's I sine of, because 15 plus 15 is the same as 2 times 15. And then 15 plus 15 plus 15 is what? Well, that's 3 times 15. Okay. So if I have cosine 15 plus I sine of 15. This will then turn into 4 cubed times cosine of 2 times 15 plus 15 is 3 times 15. Right? So, because look, if you go 15 plus 15, that's equal to, well, you can factor out of 15 and go 1 plus 1. Right? So that's equal to 15 times 2. 15 plus 15 plus 15 is equal to 15 times 1 plus 1 plus 1. Which is 15 times 3. Kind of weird, huh? Okay. So the 3 in the power kind of gets sucked into the arguments. Okay, you're kind of going to just put it right there and put it right there. And at the end, you have cosine of 3 times 15 plus I sine of 3 times 15. Of course, you know, when you wrote it out, you wouldn't write 3, you'd just write 45. Okay, so this would be 4 cubed times cosine, but we're looking for a pattern, right? This I sine of 45. Okay. So what is the pattern? In general, then, our pattern for taking some z and raising it to some power, like n, you're going to end up with r to the n times cosine of n times theta plus I sine of n times theta. Okay, so let's do one of those. and see how it works. So number 57, they want us to write our answer in rectangular form. So put answer in A plus BI form. Okay, but anyways, 57, they want us to take 1/2 times cosine of pi over 12 plus I sine of pi over 12 and raise all of that to the 6th power. Okay. So first you just raise 1/2 to the 6th power. So that'll be 1/2 times 1/2 is 1/4, then 1/8, then 1/16, then 1/32, then 1/64. So 1/64. And then you have cosine of 6 times pi over 12, which is 6 pi over 12, which is just pi over 2, plus I sine of 6 times pi over 12, which again is pi over 2, right? Because I'm taking 1/2 and raising it to the 6th power. Maybe I should write that out for you. 1/2 raised to the 6th power times cosine of 6 times pi over 12 plus I times sine of 6 times pi over 12. And those 6 times pi over 12s become the pi over 2s that you're seeing. Then to get to rectangular form, you just evaluate. So this will be 1/64 times cosine of pi over 2 is 0. Sine of pi over 2 is 1, so 0 plus I. And when you distribute, you get 0 plus 1/64 I. Okay? So the A value is 0, the B value is 1/64. You could usually write that just as 1/64 I. Okay. Okay. Do we need one more of those? Sure. Let's do one more just to be safe. And then we have kind of one sort of crazy topic, which hopefully will blow your mind. Okay. Anyway, 61, we have 1 plus I to the 5th power. And we want to sort of use the polar form to multiply that out. So what you don't want to do here is literally FOIL 5 times, right? That's just going to be a nightmare. So it's better to convert first to polar and then use our sort of general formula for taking the 5th power. So in this case, what are we looking at? Tan of theta, 1 plus I is in the first quadrant. So we have 1 over 1, and so theta will be pi over 4. The modulus R is going to be 1 squared plus 1 squared, which is root 2. So this will equal the modulus root 2 times cosine of pi over 4 plus I sine of pi over 4, all this raised to the 5th power. Okay, so root 2 to the 5th power is really, so root 2 to the 5th, if you literally, you can write it out. There's 1, 2, 3, 4, 5 of them. So this will be root 4, which is 2. This is root 4, which is 2, times root 2. So that would be 4 root 2. And then we have cosine of 5. So you're just taking those 5s and multiplying them times the pi over 4s. 5 pi over 4 plus I sine of 5 pi over 4. And then we can evaluate those to get it back in the rectangular form if that's what's required. So you get 4 root 2 times cosine. So 5 pi over 4 is where? 1, 2, 3, 4, 5. So sine and cosine are both negative. Root 2 over 2's. And then finally we just distribute. So 4 root 2 times root 2 over 2. The 2 will go in the 4 2 times. And then I'll have 2 root 2 times root 2, which will be 2 root 4, which is 2 times 2, which is negative 4. So negative 4, and then it's the same in both cases, minus 4i. Okay, so one heck of a lot easier than foiling the heck out of that thing. 1 plus I times 1 plus I times 1 plus I times 1 plus I times 1 plus I. Okay. Anyways, the next section is kind of weird, but it is really interesting. And anyways, the deal is you'll have kind of more roots than what you normally think you have as roots. So if you're looking at x equaling x cubed equaling 1, and you want to know what the answer is, there's actually 3 answers. The cube root of 1 is going to be one of the answers, but there's going to be 2 more, believe it or not. Okay, so if you're working in the complex numbers, so we want to investigate this a bit, and hopefully we can show that there's actually 2 more answers if you're working in the complex numbers to that problem. So 7, it's basically the roots of complex numbers in polar form. So we can generate kind of a formula for this via the power formula. So from before, or from above, we had z to the n equals r to the n times cosine of n theta plus I sine of n theta, like that. Okay. So now, from this, if we just take the n and replace it with 1 over n, does it work? And it does. So we're going to have r to the 1 over n times cosine of theta over n. And instead of n times theta, 1 over n times theta, basically. And then plus I sine of 1 over n times theta. And from here, we're going to get a sort of a bunch of answers, okay, from these things, because we'll think of these as there being n of them, and the way you get them is by using the formula theta plus 2k pi over n. Okay, so it's kind of like when you're solving for your angles when we were working with, and I don't know why I used weird bracket there. My brain is on overload. It's kind of like when you're solving for multiple angles, and you'll have like theta equals, or in this case, 1 over, theta equals some angle pi plus 2 pi n. And if you multiply both sides by 1 over n, you'll get this kind of formula. So that's kind of how I stomach it. That's how I kind of think of it in my head. Where does this thing come from? This is kind of how I think of it. Okay. Right. So anyways, let's see if we can pull this off. Okay. And in general, there's going to be n roots. So there will be n roots. Okay. So let's take a look at example 9. This is actually in the book. And so we have z to the 4th equals 16 times cosine of 120 plus I sine of 120. Okay, and I want to find basically the roots of this equation. It's kind of like if you have x squared equals 9, the roots are where you take it and set it equal to 0. In other words, you get 3 and negative 3, right? And of course, you could have used the square root property and said x is plus or minus square root of 9, which is plus or minus 3. Okay, this is just the same kind of problem, except instead of basically taking square root on both sides, we're taking 4th root on both sides. And hopefully we'll be able to figure out our z value. Okay, so there's going to be 4 answers here. And I'll indicate kind of the generating formula with z sub k. So z sub k will be 16 to the 1/4 times cosine of our angle 120 plus 2 pi k all over n, which in this case is 4. Okay. And then plus I sine of 120 plus 2 pi k all over 4. And then there's going to be 4 roots. We always start at 0 for the first one. And then we'll need Z1, Z2, and Z3. Okay, so Z0, 16 to the 1/4, by the way, is 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the 4th is 16, so 16 to the 1/4 is 2. Then we have cosine of 120 plus 2 pi times k. K is 0, so you have 120 all over 4, so it'll be cosine of 30, and then plus I sine of 30. And if you want to get it into rectangular form, which I think the book wants, that'll be 2 times cosine of 30 is cosine of 1/2, which is root 3 over 2, plus I times 1/2. And distributing the 2, we'll get root 3 plus I for our first root. Okay. Second root, still have a 2 there. And then that'll be cosine of, in this case, it's 120 plus 2 pi. We want to turn that into degrees. So this thing right here, we want to think of as 2 times 180. Okay, so 360 times k. Okay, this should be 360 times k. All right, so 120 plus 360 all over 4 for our angles here. So that would be 480 divided by 4 is 120. So cosine 120 plus I sine of 120. Again, that has a reference angle of 30. It's in the second quadrant, so cosine will be negative there. Root 3 over 2, and sine, of course, is positive, 1/2 I. So it'd be negative root 3 plus I this time. Next, or did I screw that up? 120 is, oops, yeah, I did. 180 minus 120 is 60, so that would be, the reference angle is 60. So this guy, the first guy is the 1/2, and of course that'll be negative. Oops, I'm gonna have to erase all this junk too. Sorry. So the first guy is negative 1/2, and then this will be root 3 over 2 I. So we get 2 times negative 1/2 is negative 1 plus root 3 I. Okay, that makes more sense. All right, next. This time it'll be 120 plus 360 times 2 is 720, and then all over 4. So I'm going to be having to go to my calculator here soon. I believe it's going to end up being 210. Let me just verify that. 20 plus 360. No, 720. Plus 720 divided by, I hate this calculator. 120 plus 720 equals, no, 120 plus 720 equals, divided by 4, 210. That was right. So 2 times cosine of 210 plus I sine of 210. Let's be a little more careful this time. So 210 is right here about. That'll be the reference angle this time will be 30 degrees. So 2 times sine and cosine are negative. So negative root 3 over 2 minus I times 1/2. So we're going to end up with negative root 3 minus I. And then the last one. So 2 times cosine, in this case it will be 120 plus, what do we have, 360 times 3. 1080 over 4. So I'm looking at 300 plus I sine of 300 will equal 2 times, so again, let's be a little more careful about this angle. 270 is 3 pi over 2, so 300 is over here. 300 minus 360 will give you 60 for your reference angle. And so we're in the fourth quadrant. Cosine is positive, and at 60 degrees it's 1/2, so 1/2. And then sine will be negative, minus root 3 over 2i. So it'll be 1 minus root 3 I. Okay. We can plot these things, and this is where it gets kind of cool because you could see the symmetry involved if you were to plot these. So root 3 plus I is, and where are these? So it's going to start out at pi over 6, and then here's 2 pi over 6, and then 3 pi over 6, and then 4 pi over 6, and 5 pi over 6. Okay, so the first one is going to be on pi over 6 at 2. So they're all located on the second concentric circle. Of course, I just accidentally erased my pi over 6. It's right there. So the first one is here, and then the second one is at 120 degrees. So that would be right here. And you see how they're perfectly 90 degrees away from each other. So you can almost predict the next one is here, and then the last one is here. And that turns out to be the case. Right? So it's kind of cool. Makes a little picture. And let's go back to this question up here. What is the cube root of 1? Okay, so let's say we have, and kind of set it up the same way, z cubed equals 1, and where is that? That's the same as 1 plus 0i. It's located right here. So I'm predicting that we're going to have 2 more kind of answers in the imaginary plane, one here and one here. Okay. So anyways, rewriting this as in the polar form, so this would be 1 cubed there, I guess. How did that work? So it's just, well, z cubed is just 1. Okay, there's no cube in there. Cube is 1. I want to put it in polar form then, so tan of theta is 0 over 1, which is 0. So this will be, the modulus, of course, r is just 1. So it's going to be 1 times cosine of 0 plus I sine of 0. And then the cube root of that would be 1 to the 1/3 times cosine of 0 plus, let's keep it in radians this time. I'm just better at radians. 2 pi k all over n, which in this case is 3, plus I times the sine of 0 plus 2 pi k all over 3. Okay, so that would be kind of our generating formula, z sub k. So let's look at z sub 0, and we should just get 1 for this one, right? So this is 1 to the 1/3, of course, is 1 in the real numbers. And then we have times cosine of 0 plus 2 pi times 0, so that's just 0, plus I sine of 0, which of course is just 1. Okay. Z sub 1, and then there's other answers. Z sub 1 is 1 times cosine of 0 plus 2 pi all over 3. So that would be 2 pi over 3 plus I sine of 2 pi over 3. And then that will equal You can just distribute the 1, and then cosine of 2 pi over 3. Where are you? That's in the second quadrant, so cosine is negative, and that'll be negative 1/2, and then plus I, so sine is positive, and it'll be root 3 over 2 right there. Okay, and then z sub 2, so another answer, will be 1 times cosine of 0 plus 2 pi times 2, so 4 pi all over 3, plus I sine of 4 pi over 3, which of course will give you this time, there's 2 pi over 3, 3 pi over 3, 4 pi over 3 is down here. Okay, so we're going to get two negatives, right? So negative 1/2, and then minus root 3 over 2, and this should be I in both cases. Okay, so you get 3 answers on the basically the unit circle. Okay, so you have a pi over 3 right here, and kind of to give us the 4 pi over 3, it'll be right there. So the unit circle will be like this. Okay, so one root is the root we all know, which is at 1 on the real numbers, in the real numbers. But if you extend it to the complex numbers, there's actually 2 other roots. This guy right here, and this guy right here. Kind of crazy, huh? I mean, you didn't know that until now, probably, unless you're watching math videos all day long. Okay, so pretty cool stuff. We'll leave it at that, and let you go on with your day. And thank you for watching as usual, and we will see you next time.